Welcome back, everybody. Learning as a hobby. In this video, I want to actually continue with Taylor's classical mechanics because I want to actually make sort of a push to get to chapter 2 already because I'm starting to feel antsy and I want to get moving along in the book. So um, I think the next two videos, well, the next two videos will be section 1.6 in this, and then I want to the video I'll do after that will be section 1.7, which is the last section in chapter 1, just so I can finish chapter 1. I kind of feel like I just want to get it passed, and then so we can move on to chapter 2. And then I'll get back to the other books. So let's do that. This video is gonna be let me share my screen. This video is going to be for section just for the oops, what did I just do? Is for the summary of section 1.6 in the book, which is a very short section, so this shouldn't take very long. And then I'll make the video right after this of the exercises because I've already finished them. So, all right, like I said, this is a very short section. Basically, all he does in this section is say that if you're solving a mechanics problem using Newton's second law and it's written in Cartesian coordinates, then the differential equations that you get are solving the problem using Newton's second law is equivalent to solving 3 second order linear ordinary differential equations. And that's because Cartesian coordinates, the unit vectors are constant. So when you differentiate them, they go to 0. So it gives you a particularly easy form, I guess, for the derivatives of the position and the velocity and so on. So here, just saying that over, the position vector r of a particle written in Cartesian coordinates is particularly easy to differentiate since the unit coordinate vectors are constant. So just like I said, so in other words, if r is x hat plus y hat plus z hat, where x hat, y hat, z hat are the unit vectors in those respective directions, then you can see here if you differentiate, you get, it's very simple. You just differentiate the coordinates in that direction. So, for example, the velocity of the particle or the object, whatever it is just the velocity in the x direction times x hat plus the velocity in the y direction times y hat, and so on. And same thing for the acceleration. Right. So again, it's just very easy to differentiate those vectors if you're in Cartesian coordinates. In section 1.7, we're going to do it in polar coordinates, which is more difficult because the unit vectors are not constant with respect to time. So that's what we'll do in the next section. But anyways, going back to this section, so here, let F be the total force acting on a particle. Then Newton's second law says F equals m times a, or in other words, F equals m times the acceleration. Right? If you write this out in its vector form, the left-hand side is the part of the force in the x direction times x hat plus the part of the force in the y direction times y hat, etc., etc. And on the right hand side, you get the mass. Oh, did I forget to write the mass here? I think I did. Let me fix that. So there should be, whoops, there should be m here, there should be m here, and there should be m here. I just forgot to write that in. All right. So this is just the long way of writing that, right? Okay, so because of that, you can set the components equal to each other. So set this equal to that, set this equal to that, set this equal to that, and you get 3 linear second order ordinary differential equations whose form is identical to each other, which just the variables switched out, right? So the first one involves the variable x, the second one involves the variable y, et cetera, et cetera. So solving the mechanics problem using, oops, using Newton's second law is, if you're in Cartesian coordinates, is equivalent to solving these three differential equations simultaneously, right? Which we do in the one example that he does in the book, which is a very common mechanics problem. So you have, some mass sliding down an inclined plane. So here's the problem. A block of mass m is observed accelerating from rest down an incline that has coefficient of friction mu and is at angle theta from the horizontal. How far will it travel in time t? Right, so start by drawing the picture, which we have here. So we have the mass sitting on the inclined plane here. It has mass m. The angle here is theta, right? So, and then we defined our coordinate system. The positive y-axis is normal to the plane, and the positive x-axis lies along the plane with the origin over here. Okay, the mass is sliding down this way because gravity is pulling it down over here. So we have a component of gravity in the x direction, and we have a component of gravity in the y direction. Okay, so the pull due to gravity is negative mg, right? So it's pulling straight down. The component in the x direction and in the y direction, we have to take into account theta. So the pull in the y direction, if you remember your trigonometry, is given by, so I'm talking about this vector here, would be given by negative mg, so because that's the hypotenuse of this triangle here, times cosine theta. Right, so this is the force due to gravity in the y direction. So y times the unit vector y hat. That would be the force in the y direction here. But we also have the normal force because obviously the mass doesn't fall through the plane, so you have the normal force to counteract that, right? Forces happen in equal and opposite directions. So this is the normal force, right? Notice it has the same magnitude as the force due to gravitation, due to gravity, and it has opposite direction. Okay. Let me just erase some of this clutter here. So I have that fact written down here. The normal force minus the force due to gravity has to sum to 0, right? They cancel each other out because the mass is not falling through the plane, right? And by Newton's second law, that's equal to m times d squared y over dt squared y hat. In other words, the acceleration in the y direction is 0. Okay. Then we also have to take into account the x direction. So gravity has a component in the x direction here. It's this one. And again, using trig, that would have magnitude m. So this would be in the positive x direction. So I'll write it as positive. It would be mg sine theta times x hat. So that would be the force of gravity in the x direction. Okay. And then we have the friction for the friction force due to friction. Is that the right way to say it? In the opposite direction to that's given by this, and it's proportional to the magnitude of the normal vector. The proportion, the constant of proportion is mu. So the force due to friction would be mu times the norm of the normal vector, the normal force, which would be mg cosine theta. It goes in the negative x direction too, so you need a negative sign here, times x hat, right? So that would be the force in, due to friction. So the second equation that I have down here takes that into account. So we have the force in the x direction due to gravity, which is mg sine theta, and we have the friction force, so minus mu mg cosine theta times x hat, and that by Newton's second law, that's equal to m times the acceleration in the x direction times x hat, right? We really actually don't need the vectors here, because we're gonna just solve the equations for their components, but I wrote it out just so that you could see, that these are components of a vector. So, and then finally in the z direction I'm defining to be coming out of your computer screen, and that's 0 because the puck is not, or the whatever it is not moving, side to side, right? So that acceleration is also 0. Right, and then we just solve those equations. So use our calculus. So the first equation gives us that the velocity in the y direction is constant because the acceleration is 0, but the constant is 0 because the mass is not going up or down in the y direction. It's staying constant. It's staying in the same place, right? There's no velocity in that direction, and that means that the uh, the y coordinate is also 0 because when you integrate dy dt equals 0, you get y equals a constant. But again, the mass or whatever it is not moving up or down, so that's also 0. Right. The most interesting one, and maybe I should say actually just to get out of the way, same idea for z. So z is also, the z coordinate is also 0. The only thing that's non-zero is the x coordinate. So that's where the interesting stuff is. So again, you setting up Newton's law. So you have m times the acceleration in the x direction is equal to the force. We can notice you can cancel out m on both sides, so we get dx squared dt dx x sorry d squared x over d t squared is g sine theta minus mu cosine theta, and then just integrate that with respect to time. You get a constant here, but the initial velocity was 0 because remember it said that the mass was starting at rest. So you get the velocity g times sine theta minus mu cosine theta times t, and then integrate one more time. The initial position was 0 though, so k is 0, and you get that the x coordinate is given by this function of time, 1/2 g times sine theta minus mu cosine theta t squared, and that's it. That's this function here gives you um, the position of the mass at time t, or the object, whatever it was he said it was. Right, so that's basically what he talks about in section 1.6. There are a number of exercises though for this section. So I'll do the exercises next. I'll upload this video, and then in a few minutes or so, I think I'm going to eat some dinner, and then I'll upload the problems that I did for section 1.6. All right, guys, keep learning. I'll see you in the next video.